Okay, let's begin. Last time we left off, we were doing the numerical integration of discrete data of these metric tons of CO2. We did this together in Python. We used the left point rule and the right point rule. We called that the discrete data rule, I guess. You know, it's similar to the composite, but it's really not a composite one because it's just based on the data that you have. And we compared that to TRAPZ, which is the gold standard we were going to use for comparing our results to numerically integrating discrete data in Python. And we did this together in the notebook, and I wanted to note something. One of your colleagues pointed to me that the answer he got was different than the one I have here. What was the answer? You had probably 226. Yeah, 226 or something. And the reason for that, so when you see something off like that, please point it out. Like, it doesn't mean you're wrong. Okay, actually you're not wrong. The data that you have is a little older than the data I'm using for this one. So the data I have over here goes all the way to 2018. The data you have, I think, ends at 2010 or so. So there's less data points. That's why you got a different answer. So you're correct, I'm correct, we just have different answers. But please let me know, like, don't feel embarrassed like you did something wrong or not. Okay? Sometimes, you know, these things happen, and that's okay. So that's the only reason why you have a different answer here, okay? Now, if you had 1 or 3, that's obviously, there's a mistake there. But otherwise, if you followed everything correctly, then your answer should be within this ballpark. Okay. We're about to be done with numerical integration. And so far, to recap, we looked at numerical integration of continuous, fully analytical functions that could be hard to integrate analytically by hand. And we looked at numerically integrating discrete data that is given to us. We learned 3 methods. They're the easiest methods to learn. Left point rule, right point rule, and the midpoint rule. And these 3 rules apply equally validly to any continuous function. And to get more accuracy there, you pick more points in the domain that you're integrating. That's called the composite rule. You sum up all of those little rectangular areas, and you compute the area under the curve. When we went to discrete data, the left and right point rules were very easy to apply to equally and unequally spaced data. You just pick the point on the left or the point on the right. You calculate the area of that rectangle and move on. The midpoint rule is a little bit more tricky as it requires equally spaced data, and you'd have to skip every other point, okay, to get that calculation done. Now, all of those rules, the left point, right point, midpoint, don't forget our initial premise in how we are going to approximate functions or data in order to do numerical integration. The idea was to fit a polynomial, order 0, order 1, order 2, order 3, whatever. Just fit a polynomial like we did with interpolation between 1, 2, or 3, or 4 points, and then integrate that analytically to come up with the formula. And this could work whether you have discrete data or analytical function. The left, right, and midpoint rules are the simplest examples of that, because they are polynomials of order 0. They're just constant. You pick a constant in that interval. All right, so now it's time to do, the only way we could get more accuracy, at least for continuous functions, was to put more rectangles under the curve between the integral limits, a and b. Okay? So now, fortunately, there are methods that are more accurate with less number of points or less number of rectangles. That's kind of the key question you want to ask. And the first one we start is with the trapezoidal rule. Instead of taking a constant between a and b, between that interval, what's the next approximation for a polynomial? Is a first order polynomial, which is a straight line. Okay? So the idea for this approach is between a and b, and again, this a and b is a sub-interval in a composite rule. It doesn't have to be from 0 to infinity, right? So that's really not not accurate at all. So we're thinking here you're approximating either discrete data of two closely spaced points or a continuous function, and you're splitting it into small intervals, and you're taking a and b as that small interval. And instead of taking a constant, in this case, we're going to take a straight line between points A and point B, or f of A and f of B over here. And you draw that straight line, okay? So now the approximation to the area under the curve becomes an approximation, or becomes equal, it's approximated as the area in this quadrilateral, okay? In this element over here. Okay? So that's a trapezoid, right? So this method is called a trapezoidal rule because this when you draw a straight line, it creates a trapezoid. So now just geometrically looking at this, you can compute the area analytically by hand because it's simple. What's the area of a trapezoid? Go ahead and develop that formula. Okay, let's get the trapezoidal rule just from basic geometry. Okay, so if you don't remember your geometry, what's the area of a trapezoid? It's the base times the median height, right? It's the base times the median height. Okay, so whatever you call the base, whether the vertical line or the horizontal line. Okay. Just geometry, just basic geometry. You're looking at the area of that trapezoid. That's what we're using to approximate the area under the black curve. Mechanistically, this occurred when we drew a straight line from point f of A to point f of B. Okay? We drew a straight line that gave us that trapezoid. Okay, so how would you approximate that? So the base, let's say, is B minus A, and the median height is what? F of A plus f of B over 2, right? Or f of A plus f of B times B minus A over 2, whichever way you want to look at it. Okay, so that's the area of the trapezoid. You can go back to your geometry stuff and try to remember that. And so even if you were to deduce the formula of the straight line and do the integral of that, you'll get that same answer. So that's one other way of doing it, is get the formula for that straight line, y equal ax plus b, or whatever, mx plus beta, and then get the slope and get the intercept like we did with interpolation, and then integrate that by hand. That's the advantage of doing this approach, and then you'll get this analytical formula. So that's our approximation. It's called the trapezoidal rule. It is incredibly accurate. It is very, very accurate. Just going from the midpoint rule or the left point rule to just adding 1 degree of freedom, just drawing a straight line, okay, we get more accuracy. We'll look at the error at the end. Okay? So now I'm going to ask you a question. This is a curve. My curve is y equal 2x plus 3 between a and b. And I'm asking you, what is the true error in integrating y equal 2x plus 3 using the trapezoidal rule between 0 and 2? So in other words, okay, the exact solution is the integral from 0 to 2 of 2x plus 3 dx. That's equal to 10. You can integrate that by hand. Now, if I were to approximate that with the trapezoidal rule, what's the true error? Ashton.
Would just be 0.
Why?
Because the trapezoidal rule is basically a straight line.
Yes. Yes. You're approximating a straight line with a straight line. It's going to be exact. So if you were to draw a straight line between the 2 points here, it's going to be exactly on top of that red line, the original curve. So using a trapezoidal rule to approximate a straight line, the integral under straight line is going to give you an exact answer. Okay? Those are the trick questions that I will play on you. Okay. So now, what I want you to think about, though, is there's a key advantage of the trapezoidal method. It doesn't require any more data points than the left point rule or the right point rule or the midpoint rule. It doesn't need equally spaced data, right? Because it's just takes the 2 points, the one on the left, the one on the right, and so, but you get way more accuracy than the midpoint rule or the left or right point rule. So in practice, it is the method of choice that we always use to integrate specifically discrete data, right? So let's see. Okay, here's another trick question. What is the true error in integrating y equal constant on the interval a, b using the trapezoidal rule? So now you have a constant. You use the trapezoidal rule to approximate the integral of that constant. 5? Oh, 0. Okay, let's take up some votes. So is the constant a special case of a straight line? Absolutely. It's a constant is a straight line with a slope of 0, right? Think about it. Draw a straight line between 2 points on that curve, which is a constant. It's going to fall exactly on top of that constant. So yes, the trapezoidal rule is going to integrate a constant exactly. Okay? It's just simply the area of the rectangle becomes. Okay? All right. There are more advanced methods beyond the trapezoidal rule, and we're going to talk about them. Those are Simpson's rules, but then we get into higher order polynomials. So for the Simpson's 1/3 rule, the next order polynomial for approximation is going to be a second order polynomial, which is a quadratic. And a quadratic is going to require 3 points, okay, to fit a quadratic. Remember interpolation? You have exam 2 on interpolation, so you should remember these things now. All right, so with the Simpson's 1/3 rule, you're integrating between a and b. And one thought, okay, I need to put a quadratic between a and b, so I need one more point. Okay, so one option is to pick the point in the middle so that you can fit the quadratic. You get the formula for the quadratic, do the integral by hand, and you get the following approximation for the integral of f of x between a and b, okay, using the Simpson's 1/3 rule. Delta x is this spacing between the 2 points. Okay, so delta x is b minus a over 2 because you put a point in the middle. And then you get the formula delta x over 3 for the approximation of the integral. So you're computing the area under this. It's not a quadrilateral anymore because this is a quadratic, okay? So this is curved. But you can integrate that by hand. So once you get the formula of that quadratic, you just do the integral by hand and you get this. You get delta x, or this b minus a over 2 times f of a plus 4 times this point, which is f of a plus b over 2 plus f of b. Okay? Now, this requires 3 equally spaced points, which essentially just rules it out for discrete data that are unequally spaced, similar to the midpoint rule. But still, I wouldn't use it for discrete data that's equally spaced because I would have to jump every other point. And what if I had an odd number or an even number of points, right? You can't get enough points to do the integration correctly. So I would just not use it at all for discrete data. But it could be a very effective method for a continuous function because with the continuous function, you can easily obtain this value for the point in the middle. Is this making sense? Okay. All right, so now what is the error in integrating y equal alpha x squared plus beta x plus gamma on the interval a, b using Simpson's 1/3 rule? So we're going to approximate the integral, the area under this curve with Simpson's 1/3 rule. So you could do this by integrating this analytically by hand and then applying Simpson's 1/3 rule and taking the difference. Okay? Or you can reason about it. So Simpson's rule, what does it do? What is it trying to fit between points A and B? Quadratic, right? It's trying to fit a second order polynomial. And then if you use it to approximate a second order polynomial, what are you going to get? The same exact second order polynomial, so the error will be 0. Okay? The error is going to be 0. You're fitting a quadratic with a quadratic. You're fitting a quadratic on quadratic data. It's going to be the exact function. Okay? If you're not convinced, go ahead and prove this for yourself. Integrate this by hand, get the answer, and then compare it to that formula up there. It's going to be spot on, exactly. Okay, Simpson's 3/8 rule. Now you approximate, you go to the next order polynomial, which is a cubic. So again, you see the pattern here. Instead of fitting a quadratic between a and b, we're going to fit a cubic. Now, you see how this is getting more and more accurate on the same size interval, but I'm putting points in the middle. So, you know, it's like you are doing the composite rule in a way, because you have to choose more intermediate points, but without doing the composite rule. With the cubic, you need 4 points. So we're going to pick those 2 endpoints. And without any other knowledge, we're going to pick equally spaced. I need 2 more points, so we're going to pick them equally spaced in that interval. And again, you can do the analysis by hand. You do the interpolation. You get the formula for the cubic, and you integrate that by hand. And that gives you Simpson's 3/8 rule formula. Okay? And that formula looks like this, where the integral is equal to 3 delta x over 8. And delta x is going to be this distance between these 2 points. So it's b minus a over 3. Okay, 3 delta x over 8. And then you're going to have the first point at a. I call it x0. So it should be f of a. Plus 3 times f at this point. Plus 3 times f at that point. Plus f at b. Okay? So it requires 4 equally spaced points on the interval ab. And you can create your own formula. You can say, I want to put a cubic, but I'm going to put 1 point here that's, you know, 1/4 away, and then another point that's 1/2 away. You can develop your own formula. Okay? Call it numerical methods formula, right? Yeah.
How come they didn't name it like Simpson's 4/8 rule?
It's because of that factor, 3/8.
I know, but like,
Yeah, I don't know. All right, so now, again, I ask you the same question. So now what if you were to use Simpson's 3/8 rule to fit a cubic, to approximate a cubic, the integral of a cubic? You get 0, right? You're going to get 0 because you're trying to approximate a cubic with a cubic polynomial. It's going to be exactly on it. It's going to reproduce the exact function and the exact data, so you're going to get a true error of 0. Okay? Okay, what if I want to use Simpson's 3/8 rule on a straight line? One? Thumbs up. Okay, what error do you get? Zero. Because a straight line is just a special case of a cubic. So with a cubic approximation, you're going to be spot on a straight line. Even a constant, even a quadratic. Okay? So those...
more computational costs or something like that?
Sure, but these are kind of conceptual questions, right? But yeah, if the function is behaving as a quadratic, you know, you're going to get that exactly. Okay? I have a summary table here, so this table will be very useful for you. I'll give you the formulas for the exam, but if you're in doubt, just write them out on your equation sheet, okay? After this, I have a bunch of examples. I'm not going to go through them in class, but they're like just numerical examples of approximating like the integral from 0 to 2 of e to the minus x squared dx using the midpoint, trapezoidal, and Simpson's 3/8 rule. So I go through all of the details. You should work those out. By hand, we can work them in the help sessions as well. I just don't have time to get to, I need to get to differential equations. That's more important to me than just doing these integral approximations, because eventually you're going to do this using Python. You're going to use quad, scipy.quad.integrate.quad for exact functions, and trapz for discrete data. Okay, those are the 2 methods you're going to use in practice. But because you're engineers, this is what goes on behind the scenes. So I have a bunch of examples here for you. And you can also apply these methods with a composite approach, like we said before, on the midpoint or the left point and right point rule. So you can apply trapezoidal, Simpson's 1/3, Simpson's 3/8, all of those. Okay. So this is a summary of these higher order methods. These methods give you more accuracy compared to the midpoint, left point, etc. And I already answered this question. And which of these three rules can be easily applied to discrete data, you think? The trapezoidal rule. Yes, Aaron, you were going to answer that, right? Because you only need 2 data points. Okay? And so with discrete data, it's very easy. You go from first data point, where's the next one? Draw a line, approximate that trapezoid. Go to the next trapezoid, go to the next trapezoid, and add them up. If you want to go to Simpson's 1/3, you have to skip every other point if the data is equally spaced. If it's not equally spaced, you can't do anything. And then you say, oh, I'm going to approximate, put a point in the middle. Then you're just doing more computational costs. Just use Simpson's rule. You'll get the same answer. Okay. Okay. And so I am going to skip this activity 2. Actually, I should have skipped it, but didn't synchronize. And finally, I have one slide on the error bounds with the midpoint, trapezoidal, and the Simpson's 1/3 rule. So again, I don't want to go into the details of this, and you're really not responsible for this. But what you need to care about here is to think about the scale of these numbers. So the error here is only an estimate. We can't really compute the exact error in these methods. The best we can do is find an upper bound for those methods. And if n is the number of segments, you're integrating f of x between a and b with n segments. So this is the composite rule. You have 15, 20, 100 intervals. Okay? And if f double prime, the second derivative, is bounded by some value k. So however the function is changing between a and b, what this means, it says the second derivative or the third derivative or the fourth derivative, the maximum value of that is some fixed finite value. That's all you need to know. Okay, so remember the Taylor series when we said the truncation error is always bounded by some number. So because these functions, they don't just blow up to infinity. They're finite functions. They're not going to go to an infinite value. They behave nicely, right? So their second and third derivatives, fourth derivatives, they're all continuous, and they have an upper bound value. So that's very helpful in finding the bounds for these errors. What we find is that the error in the midpoint rule is bounded, so less than or equal to this k value. So we don't care really about the k value. All we care about is that it's a finite number, okay, times b minus a cubed over 24n squared. So you can see how the error decreases as n is increased, okay? But it changes as 1 over n squared. Now the trapezoidal rule is just about the same as the midpoint rule. As n approaches infinity, they behave the same way. But for smaller number of intervals, it's about half this one, right? It's about half this one. Now, for the Simpson's rule, look at this number, n to the power 4. So with a small number of intervals, okay, you're reducing the error by a power of 4. So it is way more accurate than the trapezoidal or the midpoint. And for continuous functions, for example, I would totally use the Simpson's rule. For the same number of intervals, you get 1 over n to the power 4. Okay? So yeah, I think I made a mistake here. So this is telling us that this is twice this error. Okay? So turns out that the midpoint is actually more accurate than the trapezoidal rule for small numbers. But as n approaches infinity, the trapezoidal rule becomes very effective. Now for discrete data, you can't use this one, just use this one, and it's about the same accuracy for large n. Okay, and that's it for numerical integration.